Let us continue coordination compounds. In the coordination compound, we will discuss geometrical isomerisms. In the geometrical isomerism, we will take square planar complexes. In the square planar complex, we will take a compound PT NH3 twice Cl NO2. We have taken so and so. Now this platinum, it is platinum. Its oxidation number is +2 and the coordination number is 4 here. Why coordination number is 4? NH3 is monodendral ligand, Cl is monodendral ligand, NO2 also monodendral ligand. Therefore, coordination number 4. Coordination number 4 means two complexes possible. One is tetrahedral, another one is square planar. It is coming under what in the sense? Platinum +2 coordination number 4 means square planar only possible. Okay. It is platinum +2 oxidation number, coordination number 4, therefore square planar only possible. Okay. Now we will write platinum, okay, square planar 4 coordination number. Now we will write NH3 adjacent, to NH3 we will write adjacent, and Cl NO2 we have written. It is one complex. Another complex we will write platinum and the coordination number 4. NH3 we will write across. NH3 will write across Cl and NO2. Cl and NO2. Okay, we have written like this. Now we have written two isomers, both have same molecular formula. Here NH3, say similar ligands are on same side or on adjacent side, therefore it is cis. Similar ligands are on across opposite side, therefore it is called trans. So cis trans isomerism is possible, therefore geometrical isomerism possible for this compound. For this compound we can say geometrical isomerism. Okay, let us take next compound PT NH3 twice, SCN twice. This complex we will take. Will it show geometrical isomerism or not? We'll see. Now we'll take platinum. Here platinum central metal, its oxidation number is +2. Therefore square planar complex it is. Here SCN we will write like this. SCN we are writing like this. SCN. NH3 will write like this. NH3 we have written like this. In another case, similar ligands will write in a opposite side. Across we will write. Across we are writing here NH3, here NH3. Now two complexes we have written. For this molecular formula we have written two isomers. Here similar ligands are on same side or adjacent side, therefore it is cis. Similar ligands are across, therefore it is a trans. So cis trans isomerism possible for this. Okay, next we will take a PT EnCl2. This complex will take. For this geometrical isomerism possible or not, we will see. Now platinum is a central metal, oxidation number is +2, coordination number is 4. Ethylene diamine is NH2 2 times will be there in ethylene diamine. CH2 will be there. It is ethylene diamine. Then we will write Cl we will write. We have written the isomer like this. For this cis trans possibility is there or not, that we have to see. Here cis trans isomerism is not possible. Why cis trans isomerism is not possible in the sense? Is not possible in the sense. Suppose if we take it is a cis, how do you give trans? Trans if you want to give, then for writing we can write like this. For writing we can write like this, but is it possible? That we have to see. For writing we have written like this, but is it possible? NH2 CH2 CH2 NH2 is called ethylene diamine, but is it possible like this? It is not possible. this will become like this only. Therefore, here we cannot say, if we say cis, we cannot say trans. Therefore, for this we cannot say geometrical isomerism. We can say that geometrical isomerism not possible for this. For this geometrical isomerism not possible. Sir. Now we will take a like this PT NH3 4 times 2 plus. Here all the ligands are same ligands. Therefore, we cannot say cis and trans. We cannot say. So no geometrical isomerism for this. Cu En twice 2 plus. This complex will take. Shall we say geometrical isomerism for this or not? We'll see. Now copper is the central metal. Oxidation number is +2. Now ethylene diamine will write. It is 1 ethylene diamine. It is 1 ethylene diamine. Another ethylene diamine will write. It is another ethylene diamine. We have written. It is a complex. Here all the donor atoms are nitrogen. All are NH2 group. Therefore, here also we cannot say cis and trans. We cannot say. So geometrical isomerism not possible for this. Next, we will take the complex is so and so. Here, 4 ligands we have taken here. One is NH3, one is NH2H, NO2. It is pyridine. It is pyridine. 4 ligands we have taken. Platinum is the central metal. Now, net charge for this complex is what in the sense +1. Therefore, we will write NO2 outside. Now, for this -1, it is 0, it is 0, it is 0. Therefore, for this +2, because here +1 is there, because here -1 is there. Now, it is square planar complex because platinum central metal, oxidation number is +2, coordination number is 4, therefore square planar. Okay. So, platinum we will write. Now, 4 ligands we will write. Now, we will write NH3. Here we will write NH2OH. Here we will write pyridine. Pyridine. Here we will write what in the sense NO2. Okay. Now, keep one ligand fixed and interchange any other 2 ligands. You will get another isomer for this. Okay. Let us fix NH3 constant. So NH3 we have fixed constant. Now we will interchange 2 ligands. Let us interchange 2 ligands. Let us interchange. Suppose pyridine and NH2OH. We are interchanging pyridine and NH2OH. Pyridine and NH2OH we are interchanging. So we are getting like this. Okay, it is one isomer. Next, keep NH3 constant and interchange any other 2 ligands. Suppose these two will interchange. We are keeping NH3 constant and we are interchanging the ligands. Here NH2OH comes. Here NO2 goes. NO2 goes. Here pyridine. Okay. Is there any more possibilities there? No more. Sorry. How do we say no more in the sense? In this case, NH3 is against pyridine. Now NH3 is against NH2H. NH3 is against NO2. So for NH3, 3 more ligands can be against. That's all. No more, isn't it? Therefore, for these 3 isomers we have written, these 3 are what in the sense geometrical isomers. How? For NH3 against pyridine, for NH3 against NH2H, NH3 against NO2. These are geometrical isomers. Okay. So we cannot say here cis trans like this. We can say that for NH3 trans is pyridine, for NH3 trans is NH2H, for NH3 trans is NO2. Like this we can say. Otherwise, for NH3 adjacent is NO2 and NH2OH. Like that we can say. Okay. So anyhow, for this, how many geometrical isomers means 3 geometrical isomers for this we said. Okay. Next we will say we'll take tetrahedral complex. Tetrahedral complex. For this geometrical isomerism, how it will be there, that we will see. Now we will take a CO, Cl2, Br2, 2 minus. We have taken so and so complex. Here cobalt oxidation number is +2. Here 4 ligands are there. Coordination number is 4. Coordination number 4 means a tetrahedral and Square planar possible. It is coming under which category in the sense tetrahedral? For this tetrahedral, geometrical isomerism possible or not, that we will see. Now central metal we have written, one ligand Cl, another ligand Cl, next ligand Br, next ligand Br, next ligand Br. Net charge is -2. Okay, we have written tetrahedral complex. We have written tetrahedral complex. Now Cl is adjacent to Cl. Both Cl are adjacent. For this Cl is adjacent to this Cl. Okay. Now we will write this one in this way. Now we will say for this complex, Cl is adjacent to this Cl. This Cl is adjacent to this Cl. Okay. These two Cl are not trans, not across. This Cl is adjacent to this Cl. Next, we will write in another manner. CO, Cl, here Cl, here Br, here Br. Okay, net charge is -2. This Cl is adjacent to this Cl. Therefore, in all the cases, chlorine atoms are adjacent to each other. In all the cases, chlorine atoms are adjacent to each other. Therefore, there is no geometrical isomerism for tetrahedral complexes. So, for tetrahedral complexes, geometrical isomerism not possible. Why is it so? For tetrahedral complexes, why do we say geometrical isomerism not possible? Because all are adjacent to each other. All the ligands are adjacent to each other in tetrahedral complexes. Therefore, geometrical isomerism is not possible. Sir. Now we will see octahedral complexes. Now we will take octahedral complexes. We will take. For octahedral complexes, geometrical isomerism possible or not, that we will see. Now we will take octahedral complex CO, NH3 4 times Cl2 plus. It is the octahedral complex. For this geometrical isomerism possible or not, we will see. Central metal will write. 4 ligands will write like this. 2 Cl will write like this. NH3 will write like this. 4 NH3 is there. So we will write 4 NH3. Net charge is +1. Here we can say square planar arrangement will say okay. Now we will say this Cl is adjacent to this Cl. This Cl is adjacent to this Cl, therefore we can say it is cis. This Cl and this Cl 90 degrees is there. This Cl is adjacent to this Cl. Similar ligands are in adjacent here. This Cl is adjacent to this Cl, therefore it is cis. Now we will say trans possibility. We will see here Cl, here Cl. Now we will write NH3 groups. Here NH3 groups we have written like this. NH3 groups. Net charge plus we will give. We will show square planar here. We have shown square planar like this. Now this Cl is against this Cl. This Cl is across to this Cl. Therefore it is a trans. So geometrical isomerism possible for this octahedral complex we can say. So, next we will take a PT NH3 4 times ClBr 2 plus. Okay, this complex we will take. This complex is octahedral complex. Here central metal platinum is having +4 oxidation state. So for this we will write geometrical isomers, central atom platinum, then 4 coordinate bonds, here Cl, here Br, and 4 NH3 will write like this. 4 NH3 we'll write like this. 4 NH3 groups like we will write like this. Here plus 2 will write. Here we can say Cl is adjacent to Br. We can say Cl is adjacent to Br. Cl is adjacent to Br. Next possibility we'll see platinum. 6 coordinate bonds will write. We'll write Cl here, Br here. NH3 4 times is there. That NH3 4 times we'll write like this. NH3 4 times. Now we will show square planar. We are showing square planar here. Now we can say this Cl is across this Br. Cl is across Br. Therefore, it is Cl is against Br. Therefore, we can say here for this complex, these two are geometrical isomers. We can say geometrical isomers. We can say. Next, we will take CO NH3 thrice Cl3. CO NH3 thrice Cl3. We will take this complex. For this complex, we will try geometrical isomerism. Now we will take CO and NH3Cl, that we will write. Cl is 3 that we have written, NH3 is 3 that we have written. We will show the square planar. We have shown the square planar. Now we can say this Cl is adjacent to this Cl, this Cl is adjacent to this Cl. This NH3 is adjacent to this NH3, this NH3 is adjacent to this NH3. Therefore, shall we say this is a cis isomer? Sir, we will try that trans isomer also we will try. Now CO we have written. Now I will write a Cl like this. Cl like this I have written. Then NH3 I will write. NH3 I will write. That square planar I will give. That square planar we are mentioning like this. Okay. Now this Cl is adjacent to this Cl. This Cl is across this Cl. Then can we say trans? No. Therefore, here we cannot say cis trans isomerism. Cis trans word we cannot say, but these two different isomers are not? Yes, because all the 3 chlorine atoms are adjacent to each other, but here all the chlorine atoms are not adjacent to each other. These 2 chlorine atoms are trans to each other, against, across. These 2 chlorine atoms adjacent, these 2 chlorine atoms adjacent. Therefore, how to say the name for, how to say, these 2 are isomers, no doubt. These 2 are isomers, but we cannot say the word cis and trans, we cannot say. Then what we can say? You join the centers of these 3 chlorine atoms. You will get just like a equilateral triangle. It is one of the phases of this octahedron. Octahedron has 8 phases. In that one phase is these 3 chlorine atoms. Another phase is these 3 NH3 atoms. So similar ligands present in the one phase of a octahedron. Therefore, it is called a facial isomer. We can say facial isomer, FAC isomer. Then this one, it is called a meridional isomer. It is called a meridional isomer. Meridional isomer. It is called MER isomer. So that this is coming under which category in the sense? FAC and MER isomer. FAC and MER isomer, if you want in octahedral, you have to take monodendral ligand 3 times. Another type of monodendral ligand 3 times you have to take. Then we will get FAC and MER isomer. We will get. We will go for next. Next one, what in the sense? CR, EN twice, BR2. Cr En twice Br2. So we are taking Cr En twice Br2 plus this complex we will take. Here we will take Cr. Now 6 coordinate bonds we have written. Now we will write Br like this, and now ethylene diamine will write ethylene diamine as 2 NH2 groups and 2 CH2 groups like this. It is another ethylene diamine. Now we can write CH2 CH2 we have written. Net charge is +1. Now these two bromines are adjacent to each other. Next possibility we'll see. Next possibility Cr. Now bromines will write across. Ethylene diamine will write one here. One ethylene diamine. Another ethylene diamine. Next net charge plus. Okay. Here Br is trans to this Br. This Br is against this Br. This Br is across this Br. Therefore, it is trans isomer. This Br is adjacent to this Br. Therefore, it is cis isomer. So, geometrical isomerism is possible. Next, we will take rhodium metal. Then ethylene diamine will take 3 times. 3 plus. We have written like this. For this geometrical isomerism possible or not, we'll see central metal rhodium. Then ethylene diamine will write like this. This is a one ethylene diamine. It is another ethylene diamine. This next ethylene diamine. So here net charge is +3. For this, all the ligands, all the donor atoms are nitrogen. Then how to say which are adjacent, which are against, which are across? Can we say? No, we cannot say. Therefore, here geometrical isomerism we cannot say. We cannot say geometrical isomerism for this. Next complex we will take Cr C2O4 thrice 3 minus. This we can write in another manner. Cr OX thrice 3 minus. OX means oxalate. Oxalate formula C2O4 2 minus. That. Now chromium we will write for 6 bonds. Coordination number 6. Oxalate will write O, C double bond O, C double bond O, O. Oxalate we have written. We will write another oxalate. Another oxalate. Next oxalate. Next oxalate. Net charge 3 minus. And here all the donor atoms are oxygen. All the donor atoms are oxygen. Then how do we say geometrical isomerism here? We cannot. So we cannot say geometrical isomerism in this case. So next we will go for optical isomerism. Next we are going for optical isomerism in the octahedral complexes. Optical isomerism in the octahedral complexes we will see. Now we will take the complex CO En thrice 3 plus. This complex we will take. For this octahedral complex, En means ethylene diamine, that is bidentate ligand. That means one ligand can make 2 dative bonds. 3 ligands means 6 dative bonds. Therefore, coordination number 6. Therefore, it is octahedral. For this octahedral, optical isomerism possible or not, that we will see. We are going for optical isomerism. So here we will take the central metal. Central metal is what means cobalt. 6 coordinate bonds. Therefore, 6 bonds I will write. Ethylene diamine I will write. This is NH2. Like this, it is NH2. Then it is NH2. Here NH2. ethylene diamond like this. Here NH2, here NH2, ethylene diamond like this, net charge 3 plus. Geometrical isomerism means mirror images should be non-superimposable. If mirror images are non-superimposable, then we can say optical isomerism is possible. Okay. So mirror images should be non-superimposable. Okay. Now we will take for this mirror image, we will take. It is mirror plane. Now cobalt I have written. Now I will write 6 bonds. How it will be there means like this will be there. Here NH2, here NH2, like this. It is ethylene diamond. Next, here NH2, here NH2, ethylene diamond like this. And here NH2, here NH2, ethylene diamond we have written like this, net charge we have written +3. So this complex we have written like this. These are mirror images. Now these two mirror images you see, are they superimposable or not? What do you say? Are they superimposable or non-superimposable? For which? How to say whether they are superimposable or non-superimposable? For which what we have to do? What you have to do means, you rotate this molecule first, rotate this mirror image, then match this one. This part should be superimposed over this part, like this you make it. Then you see rest of the parts. If the rest of the parts superimposed, then we can say these two are superimposable mirror images. Otherwise non-superimposable mirror images. Okay. So what we have to do, you rotate this and bring this one to left side, and this one will be superimposed with this one. Now rest of the things you see, rest of the things are superimposing means, then we can say these two are superimposable mirror images, otherwise non-superimposable. Now it is coming under which category? In the sense they will not superimpose with each other, they are non-superimposable mirror images. How do we say? We are rotating this one with respect to this axis. This one and this one we are making into superimpose, while these two, this one and this one will not superimpose. Why no? This will be front. This NH2 comes to front NH2 on rotation. On rotation to 180 degrees, isn't it? This NH2 will be not front, rear NH2, but this NH2, how to we take this NH2? If we take this is as a now, no, this NH2, we are rotating this 2 with respect to this axis. This NH2 will come to where, in the sense at this place it will come. Therefore, this NH2 will become front NH2, but this NH2 is back NH2. Therefore, this part and this part will not superimpose. Then similarly, this NH2 is front NH2. On rotating to 180 degree, this NH2 will go here, rear NH2. But this NH2 is front NH2. Then this part and this part will not superimpose. Therefore, these two mirror images are non-superimposable mirror images. We can call these two mirror images are non-superimposable mirror images. Therefore, it will show optical isomerism. This will show optical isomerism. Okay. Next compound we will take COEN twice Cl2 plus. This complex we will take. For this optical isomerism possible or not, we will see. Now we will take central metal CO, 4 ligands Cl we have written, then NH2 two times, it is ethylene diamine. Here NH2, NH2, it is ethylene diamine, net charge plus. For this I will write mirror image. Mirror image I am writing Cl, Cl, then NH2, NH2, ethylene diamine, NH2, NH2, ethylene diamine. Okay, net charge plus. So now this Cl is adjacent to this Cl, therefore it is cis. Here Cl is adjacent to this Cl, therefore it is also cis. Are they superimposable or not? That we will see. For which what you have to do means, first rotate this mirror image such that this Cl and this Cl, let it superimpose over this. Then you see rest of the things. If rest of the things are superimposing, then we will say superimposable, otherwise non-superimposable we can say. Okay. Sorry. Now we will try. We are rotating this to with respect to this axis 180 degree. Then 180 degree if you rotate, this Cl will come to which place? This place, no. So 90 degree rotation will do. Huh? With respect to this axis, we will rotate 90 degree. Then this Cl will come to this place. Then these two Cl and these two Cl superimposable. Now we will say this NH2 is front. This NH2 is front now. On 90 degree rotation, this NH2 will go here. This NH2 will go here. Correct? And this NH2 will be down. So this NH2 will go rear, this NH2 will be down. But here both NH2s are left side only. Therefore, they are not superimposable. Therefore, these two, that means these two are optical isomers. That means this cis form of this complex is optically active. That means transform will take now. Transform is optically active or not, we'll see. 2Cl, here NH2, here NH2, this is one ethylene diamine. Here we'll say NH2, NH2, it is one ethylene diamine. Now we have written the complex. Here plus charge. Now if you see, we have written the complex. In this complex, plane of symmetry is there. Both Cl are across to each other, therefore it is trans. Here plane of symmetry is there. How the plane should be there means, you take the plane, in that plane Cl, CO, Cl has to come. That plane, that means that plane is bisecting this molecule like this. That plane is bisecting the molecule like this. Then this part and this part, this left side part and right side part are superimposing with each other. Therefore, this is having plane of symmetry. This molecule is having plane of symmetry. So it will not show optical isomerism. Optical isomerism means elements of symmetry should be absent. Which are elements of symmetry? Plane of symmetry, center of symmetry, axis of symmetry. If these three are absent, then only we can say the compound will be chiral compound or asymmetric compound. Then that will show optical activity. That can show optical isomerism, we can say. So now we said this complex, this transform of this complex is not optically active. Okay, transform of this complex is not optically active, optically inactive because of plane of symmetry. Now we will see this complex will take. We will take this complex Cr C2O4 thrice 3 minus will take. This complex we have written like this. In this complex, it is, can it show optical activity? That you say. Here optical activity is not possible for this. Optical activity is not possible for this. For this, optical activity is possible or not, you see. For this optical activity is possibility is not there, is there or not, you see. For this For this one, optical activity is possible. For this also, optical activity is possible. Both are optically active isomers. Like this one. Here we said optically active isomers. We said no, like that only they are. Okay. Next we'll say, next we'll take a next compound we are taking. What is that means? CO NH3 4 times En. We'll take this complex. For this complex, optical activity possibility is there or not, we'll see. Optically active or not. What do you say? Now we'll take CO central metal and 6 coordinate bonds we will write, and NH3 4 times we have to write, and ethylene diamine we have to give. It is ethylene diamine. NH3 4 times I have given. NH3 4 times. Okay, net charge plus 3. Now it is optical activity possibility is there or not, we have to see. Then we will take the mirror image for this. Mirror image and this one are no doubt super impossible. Therefore, it is not optically active. It is not optically active, we can say. Sorry. Next, we will take a Cr H2O 4 times Cl2 plus. This complex we will take. This complex. Here optical activity possible or not, that we will see. Now we will take Cr H2O 4 times Cl2. Okay, Cl2. So what do you say? Here optical activity possible or not? If we take a plane like this, which is bisecting this molecule into two, then we can say left side and right side are equal. Therefore, we can say plane of symmetry is present. Sorry, now we will take like this. We are taking like this. Now, in this one, do you say plane of symmetry is present? Here we said plane of symmetry is present. We have taken a plane like this. Then left side of this plane is this one, right side of this plane is this one, equal. Therefore, this is not a, here plane of symmetry is not there, we said. Sorry, plane of symmetry is present. Therefore, it is optically inactive. What about this? Here we'll see. Here we'll take a square like this. We'll take a plane like this. We have taken a plane like this. In this plane, either side of plane, you see water. Therefore, either side of this plane, equal part is there. Therefore, plane of symmetry is present. Therefore, it is also optically inactive. Okay. So that this complex cisform or transform, none will show optical activity. Cis and trans, none will show optical activity by this compound. Okay. So this is about optical isomerism. Optical isomerism in this octahedral complexes. What about tetrahedral complexes? Will it show optical activity?